Thank you so much, Anthea, for the invitation. So I will present a joint work with Henrique Ennes about Lie groups and machine learning. So let me start saying that this is not a new topic. There is a number of studies about how to use symmetry of the data to improve machine learning tasks. So in this context, usually it's a linear action that we're interested in of Lie groups or finite groups. But when we found that something was missing in the literature, and that was a tool that could allow us to check whether the data at hand actually admits an action of the group, or even something to measure how good are these techniques to implement in our actions. So this is what I will present. I will start with a few motivations. So the typical example of Lie groups in machine learning is rotation of 2D images. And so let me show you a funny phenomenon that happens. This is an image, RGB image that I rotate. And all of these images, I convert them into a vector in order to the m times m. So this is the number of pixels times 3, the 3 channels of the image, just by flattening the image. And the point cloud you obtain in this space, the black dots, is actually highly structured. And you can see that by computing, for instance, the covariance matrix.
Sorry, one question. I think maybe on Teams you were still on the first slide. So, is there anything you can do about that? Yeah, something happened.
Something happened?
Yeah, on Teams. So now it moved. I don't know if you
So,
did
stay like that. Let me go back. Seems like there's a delay. Yeah, there's a few seconds delay.
Okay.
Should we? Do you hear me correctly? Online?
She said it's better if you stay on this side, I guess.
Okay.
Is this the microphone here? Maybe we turn it. Or wait. Yeah, no.
It's not connected. This is not
This
connected.
is not connected, no? Okay, or maybe this is the microphone, or, no, oh, no, yours, yes, so you can say here.
Right. So please tell me if you cannot hear me correctly online. I will stay close to the computer. All right, so I was saying, to understand this point cloud, what we can do is, PCA dimension reduction. You take the covariance matrix and compute the eigenvalues. And you will obtain for this point cloud, you will see that the eigenvalues come as pairs. So we have eigenplanes. And what I do here, I project the okay, we have a technical issue with the projector.
This is quite embarrassing for everyone.
That's right. Yep.
We would have someone.
That's quite strange.
Okay, good.
So here I simply take this point cloud in very high dimension and project it into the first 4 eigenplanes that I found. And what you can see is that this orbit follows a nice circle in each of these eigenplanes with a certain radius that depends on the image, the intensity of the pixels, but also a certain frequency, right? So here you have frequency 2, I think here 1, and here I take the image back. I take the point back to the actual 2D image, and we'll obtain a symmetric image, right? And actually what you can show is that this curve, this point cloud, lies very close to this curve here. Well, it's just a rotation of a certain initial image in each of the eigenplanes. Okay, and so this is an orbit of a representation of SO2 in this space. And so our algorithm tries to detect that, and so the pin curve is actually the output of the algorithm. So I will show you, I will come back to this at the end of the talk and explain how this can be useful in machine learning. But I would like to show you another example. So here we sort of expect at first to observe a representation of the circle, but you can play this game the other way around, study data that you don't know a lot about, and ask whether there is a linear action of SO2. And so this is an example with the free-body problem. So I take 3 planets, equal masses in the plane, and I let them interact under the mutual gravitational force. So it's a very famous problem. What you expect in general of this system is that it is chaotic, but in very specific configurations, the planets will follow periodic orbits. So this one is called A3. It has been found by Brook 50 years ago, numerically. And so what I do, I take these 3 planets and concatenate their position. So this gives me a vector in R6. This is this black curve, you can see. And I try to fit a representation of the circle of SO2. And I found this very nice pin curve that I can take back to the plane. I obtain a very good distance. For instance, the Hausdorff distance between the curves will be very small. I'm not claiming here that the 2 curves are equal. This will be very surprising because it will mean that this solution to the free-body problem can be expressed as a sum of sine and cosines. But it is interesting to maybe have approximate solutions sometimes. And this can be used as an exploratory tool. Okay. So let me formulate the problem we will tackle.
Okay, close enough.
Oh, yeah, right. Thank you. So we'll consider finite point clouds as inputs. And we want to find a compact Lie group, a representation of this Lie group in the Lie space, and an orbit of this representation that is as close as possible to the point cloud. Okay, so we'll introduce some of these notions in the next slides. But for the moment, so we'll focus specifically on these groups here: SO2, the circle, the torus, and SO3, the rotations of the space. And here are typical orbits of representations of these groups. This will be our input. And these are outputs of the algorithm. So we'll start with basics of Lie theory. Please interrupt me if you have any question. So Lie group, it is a manifold that is also a group. Okay. and we ask that the structures are compatible by asking that the position in the group is a smooth operation. So we have a few basic examples here. The general linear group, the space of invertible matrices, the orthogonal group, the special orthogonal group, the special orthogonal matrices. We'll be talking also about the torus. So I see the torus of dimension D as a product of D copies of SO2. Okay. Now a representation of a group. This is a homomorphism from the group to some general linear group. So you can notice that all the groups here are actually matrix groups. So this means that they are defined as a subgroup of matrices. And so for these groups, there is a canonical representation, which is simply the inclusion of the group in GLM. But you can find more fancy representations than that. So for instance, SO2, for any integer, I have this representation here. So this is turning omega times in the plane, right? So when we have a representation, what we like to do is to decompose it into irreducibles. Representation is said irreducible where it does not fix any subspace of the Euclidean space where it acts. So such a representation is called an irrep. Another important fact is that every representation of a group can be written as a sum of irreps, and by that I mean that we can decompose the Euclidean space as a direct sum of subspaces, find on each of these components an irreducible representation, such that the sum of all this representation is the initial representation. All right. So now the problem boils down to understanding the irreps of a group, and this is very well understood for these ones. So for instance, SO2, so you always have the trivial representation on R, and the other ones for SO2 are precisely these rotations of frequency omega. They all have dimension 2. For the torus, it is the same thing, but you have D coordinates, and you apply a rotation to a linear combination of these coordinates, where you have now the frequencies called weights. For SO3, you have only one irrep in each odd-dimensional vector space. And for SU2, same thing, but in addition, you have also an irrep for each dimension multiple of 4. All right. Now let me introduce the protagonist of this talk. So an orbit, you fix a representation, you pick a point in the space, and you let the group act on it via the matrices of the representation. And so this creates the orbit of the base point. Okay. So as an illustration, let's take an orbit of a representation of SO2. So it has a canonical form in 2 irreps. And you obtain the orbits will be closed curves that winds omega 1 time in the first plane, omega 2 time in the second plane, gives a sort of a torus knot, if you wish. Same thing for the torus, but now you have several tuples of frequencies, and so the orbits will be topologically tori, maybe knotted tori, but of same dimension than the group. And our last example is SO3 and SU2. So you can also decompose the representation. Generically, the orbits will have dimension 3. if you pick correctly the base point. All right. So let
Did you say all these pictures are PCA? Or how do you, why is this R5?
yeah, I reduce, yeah, always reducing the dimension of 3 to visualize. Yeah. So now we can go back to our problem. I say that we observe one of these point clouds, and we want to find the underlying representation. So the first question we have to ask is, can we even identify this representation? So this is a problem of identifiability. It is not always possible, and this is because two distinct non-equivalent representations may have the same orbits. And a very simple example is these two representations of the circle, SO2 in the plane. You know, orbits will be circles. It doesn't matter for the point cloud to turn around once or twice. So the notion we should actually consider here is not equivalence, but orbit equivalence of representations, which is simply that you can, after a change of basis, the orbits of the two representations are equal as sets. So we have a new problem of classification of representations, now up to orbit equivalence. It is not too difficult to see that. So for SO2, the orbit equivalence classes will be in correspondence with the primitive tuples of integers. So these are the tuples with trivial GCD. So kill the repetitions, the frequencies. For the torus, this generalizes as the primitive lattices. And so for SO3 and SO2, it turns out that orbit equivalence and equivalence is the same thing. All right. So now we want to study our problem up to orbit equivalence. And the main tool we will use to do that is through Lie algebras. So let me recall that every Lie group comes with a Lie algebra. So the Lie algebra, abstractly, it is a vector space endowed with an additional structure, a Lie bracket. So this is an anti-symmetric bilinear operator with another axiom that I don't even need to introduce here, because in the case of matrix groups, all of this is very explicit. If G is a subset of matrices, you can understand the Lie algebra as the tangent space of G at the identity when you see G as a submanifold of the matrices. And this bracket will be simply the commutator of matrices. All right. So let me give a few examples. For GLN, the Lie algebra, the tangent space will be the full set of matrices. And this is because GLN is an open submanifold of the matrices, so its tangent space is the full space. For SON, this will be the set of skew symmetric matrices. And same thing for the torus with a specific block diagonal form of the skew symmetric matrices. All right. And when with the Lie algebra comes an exponential map that goes from the Lie algebra to the group. And for today, it will be a surjective map. So, I mean, this notion is very close to the idea of the Riemannian exponential map, if you prefer this. All right. Very nice, we can do with Lie algebras. I take a representation of G in Rm, and what I can do is take the derivative of this representation. So it will go from the tangent space of G, the Lie algebra, to the Lie algebra of the general inner group. And it is a fact that this derived homomorphism is actually a Lie algebra homomorphism. So it respects the Lie bracket. And there is an additional very interesting thing we can do is take this Lie algebra and take its image in the matrices. Okay, so this is a subspace of matrices, a Lie subalgebra. And as it turns out, this is all the information we need to talk about orbit equivalence of representations. And by that I mean that two representations of the same group to Rn are orbit equivalent if and only if they're before the algebra are conjugate as vector subspaces. All right. So really, the space we like to work in is this quotient, the Lie algebras, Lie subalgebras of GLM up to the action of the general inner group by conjugation. All right, so we can reformulate our problem. We have the point cloud, and we would like to access to this for the algebra. And it turns out that we can do that. So I rewrote this diagram. So there is actually a space that lies between the push-forward algebra and the full set of matrices, and this is called the symmetry algebra. So let us suppose for the moment that we observe the full orbit, not only a point cloud. This is O. What I can define is the symmetry group of this orbit. So this is simply the set of matrices that stabilize the orbit. So this is a Lie group. It has a Lie algebra, and the Lie algebra is called the symmetry algebra. Okay, and you can show that it is a superset of this push-forward Lie algebra. Okay, and the good news for us is that this space we can actually estimate from the data via an algorithm that has been published 2 years ago. This is called ePCA by Cahill, Mixon and Parshall, that I will present in the next slide. So you could tell me that, well, we don't have exactly the push-forward algebra, we only have a superset. But I will show you how to get rid of, this will be a problem later. We can suppose for the moment that these two spaces are actually equal. All right, so how does this ePCA works? X will be our observation. And so the authors build this operator on the space of matrices. So it is the image of the matrix is this sum, where you can see here this term is the projection matrix on the normal space of the orbit at the point x0, xi. So in practice, we don't know the tangent space or the normal space, so we just estimate it with a local PCA, for instance. And this is the projection matrix on the line spanned by xi. Okay. Another idea is that the kernel of this operator is approximately the symmetry algebra of the orbits. Okay. I did not state formally the result, but you can say that maybe the limit of this operator, if you integrate over the orbit, will satisfy precisely this relation. In practice, we use this technique as follows. You compute the operator, then you diagonalize it, so it's a symmetric semi-definite operator. Then you have a look at the eigenvalue profile. And if you're lucky enough, you will see small eigenvalues. And so these small eigenvalues should represent somehow the kernel. They should represent the symmetry algebra. So this is an example with a sample of points on the torus in R4. I computed this. And precisely we see a symmetry algebra of dimension 2. Okay. So what the authors propose obtain the symmetry algebra is precisely to consider the space spanned by the bottom eigenvectors. You take the bottom eigenvalues and the space their eigenvectors span. So it works pretty well in practice. There is just one problem for us, and that is that this technique only estimates the symmetry algebra as if it were a vector subspace of matrices. And we don't have any guarantee regarding the Lie algebra structure. It may not be true that the bracket of elements is still in this space. And this is a problem because ultimately we would like to exponentiate this Lie algebra and reconstruct the orbits. But small discrepancies at the level of the Lie algebra after exponentiation will create huge errors. So what we have to do here is to convert this vector space, this first guess of the symmetry algebra, into an actual subalgebra. Okay, we would like to project this first guess onto the space of these subalgebras. And so this is basically the core of our algorithm. So I told you that we had this temporary hypothesis. Under this assumption, we compute through LPCA what should be the symmetry algebra. And we want to find the closest Lie subalgebra. If you have only an inclusion between these two sets, you can consider this problem instead. So you look, you seek the Lie subalgebra of GLM that minimizes this sum, that minimizes the value of the LPCA operator. So basically you look for a Lie algebra in the kernel of the operator, right? When you minimize that. And so this is what we use in general. Okay, so how to implement that on my computer? An idea would be to, embed all these spaces in a nice vector space. So for instance, we can embed the space of Lie subalgebras into the n squared times n squared matrices by, converting a linear space into the projection matrix on it. Then I can reformulate this problem, and this will give me that, where you can see three conditions here that ensures that the matrix represents a d-dimensional subspace, and we have a last condition that ensures that this subspace is a Lie subalgebra, that the commutators stay in the space. So it may look like an innocent problem, but actually there is little hope to solve like that on the computer. And this is because what is hidden here is the classification of Lie subalgebras, which is an involved combinatorial problem. So what we should do is help our computer and inject the knowledge we have about Lie subalgebras. So from now on, I will fix the group G. I will fix the candidate Lie group G, and I will only consider the Lie subalgebras that are put forward of this group. Okay. So if I rewrite my framework only for G, specified for G, then I work in this quotient space, which is precisely the orbit equivalence classes of representations of G. And for the sake of implementation, I will choose an explicit and arbitrary representative for each of these orbit equivalence class. Okay, and then I can take my problem here, specify it to G. I will end up with a formulation like that, where you can see two variables. The first one represents the orbit equivalence class of the representation, and the second one is a continuous variable that looks at the orientation of the representation of the list of algebra. So this is a discrete continuous problem, and we implemented it like that. You go through all the orbit equivalence classes of your group and solve this continuous problem each time. And then you pick the one that attained the lowest score, the lowest value. Okay. So let me. Oh yeah. Actually, we don't have to optimize over the joining group. We can only optimize over the orthogonal group with an orthogonalization step that I will present in a few slides. And so this is way better because this manifold has dimension n(-1/2). When this one has dimension n squared, it's not even it's an open. It's not a compact manifold. All right, so this is an illustration of the minimization step. I have a sample of impulse on the representation of SO2. And so the algorithm goes through all the orbit equivalence classes. Okay, for abelian groups, there is a problem that there is an infinite number of orbit equivalence classes. So I have to fix a maximal weight, which is 4 here. Then I have to optimize over the orthogonal group. It has two connected components. So this is the +1 determinant and -1. And for the illustration, I exponentiate the Lie algebra and reconstruct the orbit. And the best score is obtained here for the representation 1, 3 on the second, yeah. And we obtain a very nice fit with the point cloud. And this is an illustration of the optimization in the space of vector spaces, which, as I mentioned, in the space of skew symmetric matrices, which, as I mentioned, 6. And this is the same representation for the symmetrization for representation of SU2 in R7. You have all these representation types. I'm omitting the ones, the trivial representations. And I think here the best one is this 3, 4. And so this is the one we'll use for the algorithm. So we try to reformulate, we try to find the reductions of this optimization program. It turns out that for the circle, this is equivalent, this boils down to a Procrust problem, which has an explicit formula. So this is what we use very fast. For the torus, it reduces to the problem of simultaneous reduction of skew symmetric matrices, which is conventionally implemented as an optimization over the orthogonal group. So same thing as the main algorithm, but this optimization is way easier because you don't go through all the classes of representations and the cost function is simpler. So this is what we use. For these non-abelian groups, and we just use the formulation that I showed before. All right. Yes, this was a slide to talk about the orthogonalization step. Let me be quick on that. So it is known that every representation of a compactly group can be orthonormalized. And that means that up to a change of basis, it will take as values orthogonal matrices. Okay, and this can be done very explicitly by computing the covariance matrix and the square root of this covariance. So we use it implicitly as a preprocessing step in all our algorithm. All right, and this is finally the last technical slide. Well, the algorithm goes in 4 steps, as I told you. Now we have as an input a point cloud and a Lie group, okay, that we want to test. In practice, you can select several Lie groups and pick the best score. And so there is this normalization step that I told you. Then we compute the LPCA operator that allows to compute the symmetry algebra. We run the optimization over the orthogonal group. And so we have this last step, which consists in reconstructing the orbits. So we pick any points in this point cloud, exponentiate the Lie algebra we found, and apply it to the point. And to check whether the algorithm succeeded, we compute the Hausdorff distance between the point cloud and the estimated orbit that I wrote here. So this is not the two-sided Hausdorff distance, it's only the distance from the point cloud to the orbit. Because we don't want to measure, maybe X is not very well sampled, has no gaps between the points. And so the symmetric Hausdorff distance will also compute this that we don't want. So it's only the one-sided Hausdorff distance. All right, when the point cloud is very noisy and we don't know what initial point to choose, we have a robust version where you actually compute the orbits for all the points and then take the average of that in the measure sense, take the uniform measure on each of the orbits and take the average measure. And in this context, you can compute the Vassar's time distance between the point cloud and the average measure. All right. Let me show you just an example where this sanity check is important. So this is a synthetic data set that I generated. I embed the spatial orthogonal group into R9 by flattening the matrices. And I sampled 3,000 points on it. So I get a sample in R9, and I ask whether this point cloud is not the orbit of a representation of SO3. I compute the EPCA, and I can see 6 small eigenvalues. So it seems like the symmetry algebra has dimension 6, which is consistent with the actual isometry group of SO3, which is this product. And well, I run the generalized version of the algorithm for each representations of classes of SU2 in R9. And as you can see, 2 representations attain a very small score. If I exponentiate the output and apply it to an arbitrary point here, I will obtain for the first one a large Hausdorff distance, so the orbit is not very good. And for the second one, a very small Hausdorff distance. And so what happened here? They are both actual linear action of SO3 on this embedding, but the first one is the action by conjugation, which is not transitive on SO3. So the orbit only finds a subset of the point cloud. And this one is the action by translation, which is transitive. Okay. Yeah, so let me tell a word about theoretical guarantee. So we try to obtain a robustness result. That is something that will tell us, well, if the input is sufficiently close to an actual orbit, then the algorithm is able to find it. Right. We would like to show that this is the estimated orbit from an arbitrary point x. We would like to show that this is close to the underlying orbit. And to do that, we found that it was very convenient to work in a measure theoretic framework. So instead of a point cloud input, we can think of a measure input. And all these steps can be reformulated for measures. In the end, the goal will be to show that the Wasserstein distance is small. And so this is a nice framework because it allows us to use tools such as averaging on Lie groups. And we are able to obtain a result like that. So if the sample is close enough to the underlying orbit, so this is in the measure theoretic sense, and under a lot of technical conditions, then the algorithm succeeds in the sense that you find the correct orbit equivalence class, and we even have a bound on the proximity between the estimated orbits and the unknown orbits. So the actual theorem looks like that. We have explicit terms for all the distances involved, depending on geometric quantities associated to the objects of the problem. And these are the technical assumptions we have. Oh, all right. Okay. So let me run through the applications then. So I want to show here how this can be interesting in machine learning. So I created a data set. This is a 3D image that I rotate in the space. And for all these new images, I embed them into R times MMM, the number of pixels. Right? And what I do is this big point cloud, I reduce the dimension via PCA, dimension 10, I think. So we have a point cloud dimension 10, which comes from a collection of rotated images. And then I define here, an estimation problem. We have to define an objective function, and the objective function will be given one of these points, go back to the initial image and estimate the vector that points toward the head of this animal. So you look at the orientation of the initial image. Okay? Any objective function could work for this example. Just try to find something not too simple. So I separate it into test, training test. Okay? So this is a representation of the objective function on this point cloud. How do you solve that? Well, you can choose the machine learning technique you prefer, for instance, SVM. But we propose something different, so this is called orthogonal coordinates. If you reduce this point cloud to dimension 8 with a PCA, you will find with our algorithm that it is very close to an orbit of SO3. Okay, so this is we can describe the point cloud as an orbit of SO3, and thanks to that, we can also take the points back to the Lie algebra of SO3. Okay, given the base point and another point, what is the element here that I have to use to take one to the other? And so I can take back my objective function into this three algebra, which has dimension 3. And this is how it looks like. You know, way more separated. It looks easier to estimate. And so we train the SVM on this representation. And these are the scores. So this SVM, you can train it after reduction, after dimension reduction to dimension 3, 4 to 10. The best score is obtained by this method, you know, that only uses a 3-dimensional encoding of the data and only really the 8-dimensional information. All right, let me just say that, I mean, my point here is not to say that, oh, we had the best score, as you know, other techniques will surely do better than that. But I think it can be useful, you know, to improve already existing methods. 1 minute. All right, so we'll skip. Let's think about chemistry. Maybe, yeah, so let me comment about, so this was actually what launched the project. So there is this very interesting architecture property of neural networks that is called equivariance. So this is a neural network. Large F, capital F will be the concatenation of the first functions. And so a neural network is said equivariant when you have an action of a group on the input. So for instance, rotating the images. And that's applying this action on the input and looking into the inner layer is the same thing as already looking into the inner layer and applying another action. So the action on the input translates in the inner layers. And you know, yeah, we already only studied a specific architecture for this equivariant neural networks called steerable CNNs. And in this case, usually you're not circle equivariant. You're not rotation equivariant. You're only equivariant for a finite group of rotations. And so we ask, you know, how good are these models at implementing the full equivariance when they are only trained on maybe 2 rotations or 4 rotations or 8 rotations? And so what we did, we took an orbit of images. We look at its image into all the inner layers and applied our algorithm to check how close it was to an actual orbit of SO2. And you know, the results are what you expect. The more rotations you have in your training, the best fit you have with an actual orbit. With some interesting phenomenon I won't get into. Let me just say that. So we have an article, if you want to have a look. And we also have an implementation. This is on Henrique's GitHub. So if you want to try it, please feel free. And thank you very much.